Greetings everyone. My name is Tejasvni Dhir and my registration number is 20BCE0890. In this video, I would like to discuss Planck's concept. Here's a question that's plagued physicists for centuries. What exactly is light? For most of the 19th century, physicists believed the light was a wave, which it is, or at least light behaves like a wave when you use it in certain experiments. Then, new discoveries made them start to question that. They started getting more and more clues that light could also behave like a particle, which led to a strange concept that light was both a particle and a wave. This kickstarted the development of a major field of physics called quantum mechanics. One of the most important clues that light had to be more than just a wave was what's known as the ultraviolet catastrophe. We know how objects radiate heat. Specifically, the amount of heat they radiate over time is proportional to their temperature raised to the fourth power. But there's more going on than just this. Brings in the concept of black bodies. Black bodies are essentially the idealized version of a radiating object. No true black bodies exist, but in theory, they absorb all incoming light without reflecting any and radiate energy accordingly. Not all of the energy coming from a black body has the same intensity. You can predict the intensity of the energy coming from a black body or black body radiation based on its temperature. But when physicists came up with an equation for this intensity using the idea that light is a wave, they ran into a big problem. The equation they came up with, known as the Rayleigh-Jean's law, predicted that higher the frequency of the radiation and therefore shorter the wavelength, the higher the intensity. And that matched up experimental results really well, but only to a point. Once the frequency of light got into the ultraviolet range or higher, the Rayleigh-Jean's law didn't fit the results of experiments at all. Instead, experiments showed that black bodies had a peak intensity based on their temperature. At certain frequency, the light would be at its most intense, and after that, the intensity would actually drop as the frequency increased. The warmer the object, the higher the frequency of the peak intensity. It wasn't supposed to be this way. Even worse, if you summed up the contributions of higher and higher frequencies to calculate the total power emitted by a black body, the Rayleigh-Jean's law predicted that you'd find infinite power, which contradicts the principle of conservation of energy. This was the ultraviolet catastrophe. Something was clearly wrong with the way physicists were thinking about light. As far as they knew, intensity was only supposed to keep getting stronger as the frequency got higher. So, what were they missing? The catastrophe was resolved by an equation derived by German physicist Max Planck, an equation that basically led to the entire field of quantum mechanics. The equation, known as Planck's law, was actually very simple, but the concept it was based on was very new. Planck's law says that the electromagnetic energy takes the form of tiny discrete packets called quanta. In other words, at a certain point, you can't divide energy into anything smaller than these packets. And the energy in each quantum is equal to the frequency of the light times a very small number called Planck's constant, represented by the letter h. If you take Planck's law into account when you try to predict the intensity of a black body radiation, you end up with an equation that predicts the experimental results perfectly, including those weird peak intensities. So the ultraviolet catastrophe was resolved. Energy could only exist in discrete packets called quanta. Before, physicists thought that energy was kind of a continuous flow. But now there was this whole new idea that had physicists rethinking everything. And that was Planck's concept.